Okay, so we're going to narrow ourselves now. We're not going to do shared windows. We're going to do model sharing as in your assignment. And we're going to first just see how to implement model sharing using the generic library I talked about. And then we'll go and say that, look, hopefully we learned something general. We learned some general algorithms for sure. And if you have a general algorithm, we should also have a general abstraction. Okay? So that tomorrow, if you want to build PowerPoint sharing, you shouldn't have to repeat the two others call and stuff that you're going to be putting in an application. Okay? So how can we go and build one set of abstractions? Okay? So in class, we are looking at going from an echoer interface, which just echoes one user's lines, to an IM interface, which echoes the lines of multiple users. Okay, so this is Alice, and Alice is seeing her text echoed and Bob's text echoed. Okay, so, and in your example, in your case, you have a much fancier application. Okay, and if I was to just tell you, here's the UI, here's the demo, go implement, there's more than one way to implement. There's always more than one way to implement, but there's more than one good way to implement. Okay, so let's go and look at some good ways to implement. And if there's more than one good way to implement, that must mean that we have trade-offs. Okay, so let's go and look at the general algorithms there, look at the trade-offs, and then we'll see the general abstractions. Okay, and so let's look at the architecture. So in the single user case, I said the main constraints are that you should have model interactor separation. Whether your interactor is divided into view and controller, that's up to you. I wasn't looking at any detail beyond this level. Okay, and they all ran in one process. And we know that in multi-user applications, there are multiple processes, but are there, n processes for n users, n+1 processes? That stuff we didn't say. We know there's a session manager, okay, but beyond that, we didn't say anything else. So what happens when you go to multi-user? Okay. As I said earlier, you can just put the model in one process and each interactor in a separate process. And I said this was the least diff from the previous slide. Okay, I just had to draw some circles around the boxes I already had. Okay. And that's one architecture. And what other architecture could you have? What's the architecture you might be using that if you've thought about your current next application, what might you be thinking? Or think now? Look at the title of the slide. This is an example of
centralized on the left.
Yeah, so what would replicated be? Fred?
Maybe you'd have two models that are copies of each other, and each one just interacts with one interactor.
Okay. So they are replicas of each other?
Yeah.
They are copies initially, but they remain consistent. And because they remain consistent, they're replicas. Okay? So you're going to just have your current, okay? So we have this picture. And we know this is model sharing because the arrow goes between the models. I could have one kind of interactor here, a console-based interactor here, and a GUI here. It doesn't matter. We're going to have model sharing. Okay? Now, there are pros and cons for each architecture, but till we understand the architectures, we can't discuss about pros and cons. And that's the question that I'm going to now address. Okay? So let's look at replicated. That's what I want you to do in the next assignment. Okay? And so let's go and take our example, see what our original algorithm was for the single user architecture, and see how we can change it to do the replicated architecture. That will help us understand what the replicated architecture is all about. Okay? So originally I said for each input I should be followed by matching list edit input. Okay? List edit made in the model. List edit input is made in the interactor. List edit input occurs in the interactor. List edit made occurs in the model. List edit notified occurs in the model. List edit observed occurs in the view or the interactor. List edit displayed occurs in the interactor. So this was our algorithm. It was very simple, right? we know now that there are multiple models. Okay, so how is this algorithm going to change in the replicated case? Do all these steps still occur?
Yes.
Still occur. What else occurs, Nick?
The models need to send messages to each other in order to keep in step.
Right. So what should I do now? So let's edit this. So so that's a very general statement. That's a constraint. Okay. So when an input I occurs, what should occur after that? In the sending so there's an initiating replica. In the initiating replica, what's the next step that should occur? So the models need to keep each other consistent. This model just got changed. So what should this model do? Send a message to all the other guys. You should send maybe the same list edit. So this is one set of steps. This is another set of steps. For each replica, I should be followed by matching list edit send to others. Right? And the order of these steps could be up to you. Do you want your user to wait? Do you want to process first and then transmit? Or do you want to transmit first and then process? Okay. So this is the sending guy. What about the receiving guy? What algorithm? What's happening at that end now? That's one part of the communication. So how do I account for receipts in my algorithm? Sorry? So I have this algorithm running to send data. I need to also have something in my side to receive data, right? Which thread is going to execute that? So this could be just one thread. You could put these two steps in different threads, but this is the UI thread. For receiving messages, do you guys remember what I just talked about 5 minutes ago? What thread executes receives?
There's the OS thread.
There's the OS thread, and then there's also, maybe we don't know. Yeah, we don't know. We don't quite know, but the library, does it give you a thread? We talked about send threads. I also showed you receive threads. The library is serializing all the calls made by different users into one thread. Okay. And if it wasn't doing that, then you would have to do it yourself. Okay. So there is a receiving thread. And now can you give me the algorithm for the receiving thread?
I imagine the first thing would be a list edit receive.
Yeah.
The demonstrates we received this. Then we'd have to update our version of the model. It should be a list edit made.
So for each list edit received R, we have to do I forgot list edit made. I was cutting and pasting, and I guess I forgot the list edit made. So this should have list edit made, list edit notified, list edit observed, and list edit displayed, right? All of these things should happen. Of course, when you do made, the other actions should occur. Okay? So basically, so that our view gets changed. That's the algorithm. Okay? And I'll remember. If I don't remember, just remember there's this comma. Got it. Yeah, there should be a list edit made here. Now here's a danger. Should I do a list edit sent after this? In this case, the list edit displayed got followed by a list edit sent to others. Should the receiving thread do this? No, because? So you would get into a? How easy do you think it'll be for you to get into a loop? If you code, the obvious intuitive way, that's what's going to happen. Okay? So somehow we have to prevent this loop from happening. because we do know we're going to use the fact that list edit mates get followed by these actions. Okay, we're already doing that here, and we just have to make sure that in this case, when we do receive a method, we don't do this extra step afterwards. Okay, and that's the algorithm for that particular application. In general, there would be some kinds of edits input. Okay, this could be changing a little field in a form, it could be adding an entry, it could be changing a table. So wherever there was list edit, I've changed that to edit here. And edit basically means that the model has been changed. Okay, so this is the general replicated algorithm, which is independent of the IAM application. This could be used for PowerPoints, it could be used for editors, it can be used for anything. Okay, and again, we have to make sure that this cycle doesn't matter. Okay, so let's go and look at the real code here and see what we're doing. So when we were the single user case, input arrived, we called the observable add method in our model, which went and called the element added method in the interactor. Okay, that was what happened. What could we do here? The input arrives again, we call observable add, we go and override observable add to also send messages through the communicator to others. Okay, now what's going to happen? Some callback is going to arrive when a message arrives. It's going to be executed when a message arrives. So in some object, okay, in my coding, that's called the IAM coupler object. That then should do what? Call observable add, right? So that we can go and notify the interactor. And if I do that, what happens? Okay. So now we know what the algorithm is supposed to do. Now let's talk about an engineering thing. What should I do? I mean, I've got my history. I've changed that to replicated history, which overrides observable add to go and call two others. How should I change replicated history? Let's get down to the details. How should I avoid the cycle?
Maybe you can train it to check to see who's calling observable add.
Okay, so observable add could take as an argument a user parameter. Okay, it doesn't take right now, but we could go and change that. And we've changed the model in it, so that's good. That's one way to do it. Okay, we made it collaboration. We made the observable. We changed the signature in a we have to then go and change our interactor to understand this extra argument. So there's some substantial changes to be made, but that's good. That's one of the solutions I forgot to mention, which I wanted to talk about as the set of solutions to address this problem. Okay, and then the model then goes and says the model has to know what is its whether it's the current user or not. So the model will have to know what user it represents, right? And the model will have to be told by the interactor that this was a local change. Okay, and then it goes and compares its name with that, and it does it to others only then. So that's certainly a good, and that's something you're welcome to use that solution in your program. Okay, I was creating one set of objects for both the centralized architecture and the replicated architecture, so I didn't quite use this approach. Okay, what other approaches are possible? Supposing we don't want to add an extra argument to our observable add. We don't want to change the signature of observable add.
Okay, so what exactly is a communicator? What is its role in
So we know we have a multicast library, right?
Yes.
The multicast library provides us with the two others call that allows you to multicast. So on what object is this call invoked?
And we're invoking that on the history.
No. So history is the one that's invoking the operation.
Yes.
On what object?
Oh, yes.
okay, on something that I provide to you.
Yes.
Where we created a communicator object, in the last slide deck, and we're just invoking the two others called there. So it doesn't matter whether it's called communicator or whether there's anything. From this algorithm point of view, we have to do a two others call on some object. It has to go across the network. Okay, I'm just making it concrete by saying that in group messages, that object happens to be called the communicator.
Okay.
And we can't change that. That's provided to us. So what we can change is the replicated history. Okay, and what Fred suggested was that we have one operation that does both things. It either does two others or it doesn't do two others. And based on who the author of the change is, we do one or the other. If the author is ourselves, we send it to others. If the author is a remote user, we don't send it to other people. Okay, so one operation that does two things. And the dual of that would be?
Two operations do one thing.
That do, well, two operations that do two different things. So the IAM interactor is doing really not an observable add, it's doing a replicated observable add. Right? So that's what it's doing. We know it's a replicated operation. And so it sends it to others. It does it to others on the communicator. Right? And object received, it has to go and update replicated history. What method should it call now?
Observable add.
Okay. And so we've solved the problem. And the names now mean the right thing. If we are going to change, I like this solution better than Fred's solution because why do you think, Fred? Do you think this is a better solution?
Yeah.
Why?
Because I mean, it's kind of hassle to include an extra parameter. Just call it a different method.
If we are going to change the interactor, let's just call a different method rather than pass the parameter. The model doesn't need the parameter other than to figure out whether to do replicate or not replicate. So we can just do this. Okay? The flip side is, so each write method in general, this is having to do with add. You guys have to go and pass status information also, okay, if you've done the extra credit. So each write method has a single user version and a replicated version. Okay? Both notify observers. Local input triggers a replicated version. Remote input triggers a single user version. Okay? That's the general idea. Okay? So this is a little ugly. It's clean and it's ugly. Okay? We didn't have to have an extra parameter, but now I have to have set P, replicated set P. It gets to be an issue. That we have a lot of methods. Any other solution somebody can think of to avoid infinite cycle? Especially, and this becomes especially a problem if we're using existing objects, which don't take parameters, which don't have replicated and non-replicated versions. How can we avoid the cycle? So one approach, of course, which Fred was saying was that somehow we know who made the change. And based on who made the change, we do one thing or the other. Supposing we just get the change, we just look at the change. Does that change have enough information for us to determine whether it should be applied here or not? Supposing the change is a property value change. That Alice's status has changed from, is now typing. And this happens to be a bean. Can I know whether to go and call the set status method or not?
Maybe if it's not going to cause any change, then
Maybe if it's not going to cause any change, we don't make the change. We can call the get method on Alice's object and say, what is your current status? It says, I'm typing. And so it just doesn't go and change it. Okay? And that's a solution you can use when you have existing objects. Okay? So can detect if incoming event has been processed before. So input occurs, you do an observable add, that does it to others, that does object received, that does observable add, That sends to others again. So we have some extra messages going on here. A response comes, and from this response we figured out, oh, the state that has been sent here is equivalent. It will not cause any change here, so we just don't go and call observable add again. Okay, so we did get an extra round of messages, but we stopped after that. Okay, and then the trick becomes, how do I know there's enough information here or not to make the change? And so notification has information about old state of changed object, and that old state could be compared against the state of this thing, and if the states are not the same, so this object is at old state or new state. Okay, so that's the whole idea. You can determine if the object on which you want to make the change is at old state or new state, and write method not called if object is at new state. Okay, and just to make this all concrete, so if you have properties, receive message contains new property value, which can be compared with the property value, existing property value, and do not call it method, assuming no side effects. Okay. Otherwise, if there are side effects, if you go and send out an email in a setter, then maybe multiple set methods should be called. And here what we are saying is not from a remote site, but this is a general principle we can apply, that whenever some external object changes, we don't make the change if the property is the same value. And if you use it generally, then we have to assume no side effects. If you're sending a key value, a value pair, okay, then again we can look at the old key, a value with the old key, and not send the value. What about list? How do we determine if a list add should be invoked or not? With properties and key value pairs, it's okay. We can just check the old value. We can send the whole list. Can we do something more efficient than sending the whole list? Assume there's no concurrent values, because with their concurrent values, we are anyway concurrent input. We are anyway in trouble. So I can certainly send the whole list in the old state, and then compare the current state of the list with the old list. What else? Can I? Yeah.
Maybe you can attach like a variable to the list that keeps track of the last time it was updated.
So time. What does time mean here?
I don't know.
So maybe instead of like a timestamp on like when it was last updated, what the last update was.
Okay, and if they happen in sequence,
Yeah, and so we can, if we have enough information to say the last update was adding element A at position B after element C.
Okay, so that's getting a little long. Is there a single number I can send?
Oh, we could just have, we could assign like a unique ID to each change.
Okay.
And that gets passed around.
Okay, something simpler than that. A unique ID you can send a unique ID. You can send the last operation and its preceding operation. This is a list. This is a variable length list.
Size.
Maybe just a size. If we are at the old size, then we're okay.
Assuming the operation changes the size. What if the operation is like an in-place substitution of one of the elements?
Okay, so if it's an in-place substitution of the elements, then we can just send the old value of the element. It's just like the key value pair issue and the property value. We just go in. The operation will say that I change index I to the value k. I can just query the old value and see what it's just like the property change situation and the key change. Okay, so yeah, you're right. In that case, we just used this scheme. When we add or delete, we just send the size. Okay. Okay, I should not say do not call write method. I should say do not call add or delete method. For replace method, we use the same solution as this one. Okay.
Maybe this is kind of ridiculous, but is it possible if we use if we do it based on size, then other commands can go in and cause a loop tab? Size might be changed.
If there are if things get added in the same order, then the size will grow first and shrink later. And so it's not as if an add and delete will cancel each other. You will receive both the adds and deletes in the same order. So I believe it'll be okay. So that's why I said don't worry too much about concurrent input right now, because that will cause other problems anyway. I'm not recommending this solution. Yeah, I'm recommending you to change your code. Yeah, but I'm saying if you have existing objects and you can't change your code, then you just have to quote unquote do heuristics, which means things might not work. Yeah, and you're saying, well, if this under these conditions the application will run just fine, and under those conditions, other conditions won't run. And how to go? One of the biggest challenges in this whole area is how to take existing applications and make them collaborative. Okay, so this is sort of a solution in addressing that problem to some degree. Okay, and of course, if you have locking, then we'll make sure that things don't, you can't have concurrent input that with an add, canceling, a delete. That every object will have the same sequence of operations, so size will first grow, then will shrink. Okay. Okay, and I told you that there are these extra 2 steps, and that's what's happening in this replicated architecture. Okay, so the next topic is, now that we understand the replicated architecture, the next topic is what are the problems it causes? Okay, we saw that one of the problems it could cause is if we have existing objects, how do we make sure that we don't have cycles? Okay, assume we've addressed that problem. Here's a general algorithm. Any other problems you can imagine occurring? Because we're going to talk next about the centralized architecture. There's no point talking about the centralized architecture if our replicated architecture is just fine. And we're going to talk in depth next time, but I just want to, by now you've seen everything you need to see for your assignment. Okay, so now once I solve the query issue, we should be fine. So now I can, at leisure talk about some of the theory here. So what problems do you think can occur? Very few implementations provide replicated architecture. What about the demos? What are the various demos we saw? In some of the demos, we were solving certain problems, right? So what were the 2 problems that we saw in the demos that were solved? That is caused in replicated architecture. Okay, what are the demos you saw? There was the IM tool, then the shared window tool, jitter tool. What other demos do you remember? Sorry? Causality. That's caused by multiple operations being executed, without a serializer, and operation transformation. So these are problems that are caused in replicated architecture. These are kernel consistency. Okay. So there's consistency issues of causality and concurrent operations. And what we'll do next time is show that these are not the only 2 kinds of issues. There are other issues too, and we'll go in depth into those. Okay. So there's many ways to do your project. There are many ways to build collaborative applications in general. Okay, and one of these ways, and we don't want to just do ad hoc way. Okay, we've got it working. Okay, you needn't have taken this course to get things working in an ad hoc way. You could just ask questions on Stack Overflow. I need this task done. You get some magic code. You don't understand what it does, and it works. When it's very interesting. This is a generational thing. When I grew up in the dark ages, you tended to code yourself everything, and object-oriented languages came around, and people were reusing, and we were all very bad at reusing. We just did not want to reuse code. That's how we grew up. Okay, and all these OO people kept saying, reuse. Your productivity, your quality as an employee should depend on how much you have reused rather than how much you've written. And now we've come to a stage where people just say, why should I think? If this is a problem that I have, I'm sure somebody else must have had it before. So let's just go to Stack Overflow, look up the code. And to be very honest, when I'm in a hurry, that's exactly what I do. Right? I have to get some things done, and I say, okay, I don't know how to read from this file to this stream to this, that, to that. And let's just look up the code and copy it, compiles, runs, beautiful. Okay? And but then, when you're teaching something in a course, you do want, what if you have to do something for the first time, right? I mean, you should be the guys, as people who are doing masters and PhDs, you should be the guys who are answering those Stack Overflow questions, not the ones who are looking up, right? So we want to do things not in an ad hoc way. We want to do things in an organized way. That's why when I give you algorithms, I give you the algorithm for a specific example, and then I give you an algorithm for the general class of things. Okay, and when I ask you exam questions, I'm not going to ask you to do maybe I will, but I'm not just going to ask you to focus on this particular application demo that you've done. I'll say, okay, maybe we are doing something else now, and tell me how to solve the problem. Okay, so we realized there were some general principles that if we have divided our application into a model and interactor, okay, and we want to make it shareable, one way is to replicate the model. And interactors, anyway, every user will have their own interactor. They're not replicas. They could be very different. This interactor could be very different from this interactor. They don't have to be the same at all. What has to happen for consistency is that the models have to be the same. And based on the model, this interactor should show the same data as this interactor, though each interactor could show things in its own way. Okay? So that was a general principle, and we saw how to do that in the particular example that I do in class. You will extend that to do the extended application in your assignment, okay? And I also give you a general algorithm, right? So let's go and figure out now what the limits are for this particular algorithm. This is not the only way to do things. I will tell you the centralized approach later. There must be a reason for doing the centralized approach. So let us try to figure out what are the cons and pros of this approach. Pros, to see why we need this approach as opposed to centralized. Cons, to see why we need centralized as opposed to replicate. Okay, and so that's the goal. Okay, but the basic principle here was that you started off with this application with a model and interactor. We wanted really to have multiple interactors to a single logical model. Okay, and that logical model was going to be represented by multiple physical models. Okay, so it's just that in your machine you have multiple replicas, but conceptually they're all the same thing. That's what we want to simulate. Okay, and when I talk of drawbacks, we'll see how good was that simulation. We did some things that they seem to work for our example. They seem to make sure that all the models are consistent. And the algorithm was that basically, so the algorithm was that basically, I think I've got some underlines. Okay, so let's look at the algorithm and see what the problems might be. So can you see, I gave you a general algorithm. That was the picture that I gave you. Pictures are very abstract. They're worth 1,000 words, but they sometimes need 1,000 words to explain, to be precise. So here's the algorithm. Now, can you find flaws in it? Can you find flaws that prevent the multiple physical models from representing a single logical model? And in general, what we are saying is that, if you have an edit of some kind, a write of some kind from the user, we go and make that write on the local model, okay? And then we do some things locally, okay, which is fine. And we take this particular write and send it out to other sites. Each of these sites receives that change, makes the same change on its physical model, and then some side effects occur at that place, which cause the display to be changed. So assuming the models are consistent, we don't have to worry about the notified, observed, displayed stuff. That's going to be correct. So what we have to make sure is that we are indeed getting consistent models by broadcasting the edits. So what are we really guaranteeing? What are we guaranteeing about each model?
Very little. It seems we're not making any guarantees that these models will be consistent with each other, although we'd like to.
We'd like them to be consistent.
They will be consistent, but at any given time, as these changes are still propagating.
Okay, so at any time when things are in flux, okay, and things might be propagating, but when we talk of consistency, we talk of eventual consistency, and what might eventual consistency mean? Because nothing is in real time. Somebody once, when I started the course, somebody said real time. I said nothing is in real time because things will take time. It will take time for something to propagate from one computer to another computer. Okay, speed of light is fast, is high, but it's not infinite, right?
Yeah, but this doesn't guarantee eventual consistency either.
Okay.
Because if we have two different physical models and two incompatible changes are made to each physical model, they can broadcast that all they want. It doesn't change the fact that they're going to be consistent now.
Okay, so you're saying they can broadcast all the operations. So what are we guaranteeing? So before we see what we're not guaranteeing, what is guaranteed in this model, in this algorithm? That every model executes.
Guaranteed every model will broadcast its operations, and every model
Will execute the broadcasted operations.
will execute broadcasts. We guarantee that every model will receive these broadcasts and attempt to operate on them.
Okay, so every model will execute the same set sequence of operations.
Set, but not sequence.
Same set of operations. That's what we're guaranteeing. That every model will execute the same set of operations, and whether these operations will succeed or throw an exception, we don't know. And can you think of an example where that's not the same as being consistent? Theoretically, that's possible, because you might want sequences of operations rather than sets of operations. Yeah.
Let's say that we have like a chat room. That this chat room object broadcasts a message whenever someone enters, and it broadcasts a message whenever someone leaves. I enter the chat room and then immediately leave. Those messages are received out of order by a different physical model, which sees me as leaving, then arriving, and now has its internal structure that I'm in the chat room when I've actually left.
Okay, say that again. I mean, that you enter the chat room,
Okay.
and you see a message, you enter, and then you leave immediately.
Yes.
So you see a message, I've left, and won't these two messages be in the same order at other places too?
Not necessarily.
Why?
I wasn't talking about messages. I was saying let's assume that this model keeps a list of who is in the room.
Fine. Oh, who is in the room? Okay.
Yeah, we don't care about people sending messages yet. It's just the model knows who is in the room.
Fine. Good.
And I interact with my physical model, and I tell it I enter the room, and then I tell it I leave the room.
Fine.
And so it broadcasts two messages.
In that, okay.
And those messages can be received out of order.
Okay, that's good. So, those messages could be received out of order. But they both came from me, right, to everybody else. And if I was to use some, so let's start making some assumptions. This algorithm assumes that everybody executes the same set of operations, okay? There's actually another assumption that I didn't make explicitly. So those of you who've done some networking, how many of you have done networking? None. Nobody? One person. So if my computer is sending two messages to your computer, is there a chance that they might get reversed when you receive them? But if I'm using some network layer, are there network layers that guarantee that they will be received in the same order? Yes. So if I'm using UDP, they can indeed be received out of order. And what Nick says is perfect. if I'm using TCP/IP underneath, then they will be received in order. Okay? So let's assume for now that our algorithm is implemented on top of reliable in-order unicast. Can you think of a problem now? Indeed, if I was to implement this on top of UDP, we can have the problem that my display says that I entered and left, and your display would say that I left and then entered. Again, think of the demos I showed you.
If two different, they have one share of a topic object, and one person just delete some characters
Yes.
in his local physical model, and the other guys didn't see the change, and he also deleted it. But before the delete message operate on his machine, he received that other guys have already deleted that, so he will delete another character, but not the one he want to delete.
Beautiful, beautiful. Okay. So the problem is that we both deleted the same character. Okay, and you deleted the character because is that a practical example? I have a typo. Both of you notice that I have a typo. You delete the S. Your deletion hasn't gone to the other person. The third person deletes the same S. And now, what's going to happen? When the delete operation is sent to the other side, it'll either fail because that character doesn't even exist, or it'll delete another operation. Okay? And that happened because all of us did not execute the same sequence of operations. And it's because of the cheating we did right here that we went and made the edit and then notified and displayed it before agreeing on a global order. Okay? We saw some causality problems also, okay, which can cause similar issues. Okay? So this is the problem, that these edits we are just executing this, guaranteeing the same set of operations and not the same sequence. Okay? And we will deal with this problem later. Okay? So in future assignments, we'll go and overcome this problem to some degree. Okay? Let's move this thing away so that you can see the bottom. Okay. So let me say that we somehow by magic make it look as if each physical model is executing the same sequence of operations. Okay, we can do some magic. We can say whether these two operations commute. It doesn't matter which order they execute in, so we won't do anything for them. If these two operations don't commute, we'll do some operation transformation. We'll do magic stuff. Okay, we might even have concurrency control to make sure that only one person executes at any one time, so that when I make a mistake, then I give the lock to you, you fix it, and somebody else does it. Okay? If I guarantee this, are we still fine? Or will the replicated situation be bad?
Well, you said we're using TCP. Are we using TCP?
Let me not commit to anything. Let me just say that we guarantee somehow by magic. Okay, and because what we're doing is multicast. Multicast can be, and we'll do some kind of, I shouldn't call it reliable multicast, we won't really do it, but we'll make it look as if it's reliable multicast. Whether reliable multicast is built on top of reliable unicast, we'll just punt that issue. Okay, and let's assume by magic, we can assume that each model executes the same sequence of operations. Can we run into trouble? Still. The models will be consistent. Can we run into some other kind of problem? Can we run into any performance issues? And correctness issues. So before I go into that, I thought I had another slide. Is executing the same operation, an operation once, equal to executing this operation multiple times? In one case, what you really want to do is assume that the multiple physical models represent one logical model, right? If I had only one physical model, an operation would be executed only once. When I have multiple physical models, the same operation is executed multiple times. Is the result of executing multiple operations the same as executing the operation once? If I do an add 2 and 3, if I do it once, I get 5. If I do it 10 times, I still get each time 5. So in that case, it works. And add is a pretty trivial operation. Okay? So can you imagine some performance problems when you execute the same operation multiple times? I said add is a trivial operation, which means it doesn't take much time to execute.
What if the operation that that we're performing multiple times is non-deterministic or has like a race condition?
Okay, so that's good. If it's non-deterministic, what does non-deterministic mean?
It's not guaranteed to have the same output every time you run it.
Okay, can you think of an example of a non-deterministic operation?
A random number generator.
Okay, random number generator. So that's a correctness issue now, right? That different interactors are going to see different results now, even though the models execute the same operations. If they store their value, they're not even consistent. Okay, so even if we guarantee the same sequence of operations, it's not guaranteeing consistency of the models. Okay, so that's correctness. Let's think of performance a little bit. I input n, and I find the prime factors of n. Is that a hard problem? How hard is it?
NP hard?
NP complete, NP hard, very good. Where did you study that stuff? In which course? Or did you study this in a course?
We might have touched on it in 3A1.
Okay. Is that the algorithm course?
No.
Oh, is that the...
I haven't taken the algorithms course.
Okay, okay. So, all your security guys, right? You're all taking cryptography this semester, right? So cryptography is based on this. The whole idea is that this is very hard to, given two prime factors, we can verify that they are indeed prime factors of a number. So if you could somehow, by magic, figure out what the two prime factors are, non-deterministically, then in polynomial time we can figure out they are indeed the prime factors, but to figure out whether they are prime factors or not takes a long time. Okay, and now what are we doing? Finding it once takes a long time, and what are we doing? We are making n computers compute prime factors. Okay, so from performance point of view, people always say, oh, replicated architecture is always more efficient, and maybe not. Okay, and so we have inefficient replicated computations, and the reason why we often do replicate it is because we get local response. Okay, we don't have to go over the network. Just balance going over the network to the computation time. Okay, so there's computation versus communication costs. Okay, and you have to figure out that, okay, it's okay to replicate. Otherwise, we'll just centralize it, and it's going to take forever anyway. Okay, and just to give you guys an example of how this can be important, when I was a research assistant at Madison, Wisconsin, where I was a grad student, we built our own distributed operating system. It was the world's most flexible operating system built, I think. It was also the world's slowest operating system. Okay, it took 20 milliseconds for messages to go just within the same computer. Okay, there were so many layers of abstraction. So this was funded by DARPA, and DARPA came to sort of see our fast operating system working. And they had to show some application that would run fast. And I had developed a distributed checkers program. Checkers takes a long time to compute moves. So it was indeed good to go and distribute the computation across multiple computers, no matter how long the communication cost was. And we got linear speed up just because the computation was so high. Okay? So that's when distributed computing really could be used for making faster computation. So I'm just saying that that was an example where it's a different kind of example, but the same kind of trade-off being made between communication and computation. Okay? So maybe in this case, we won't go for replicated architecture. Maybe we'll go for centralized architecture. Whatever that is, we'll go and see what that is next time. I mean, soon, okay, in the next phase. And now, can you see a performance problem here that I have? So maybe we don't do compute, prime factors. Those are these security and numerical guys. We are systems guys. We do simple things. We are systems guys. Maybe we read files. Okay. So here's an application that loads a file. And can you see a problem when we have replicated?
Well, one, there's a performance issue, and that loading the file can take a while, and every model has to load the file. And two, the file can change between reads.
Okay. So there's so there's two problems. Okay, firstly, accessing a file for single user or collaborative is slow. Okay, we hope that the operating system has cached data, that's fast enough. And now what's happening is that there are multiple replicas accessing the file at the same time. Suddenly, that operation becomes there's a bottleneck condition. And what Nick is saying is that, well, what if the file changes in between? Well, writes is yet another issue. Okay, and we'll deal with that. We'll get to writes pretty soon. Okay, writes will create even bigger problems. Okay, so again, this is a performance issue that we have a bottleneck, and it's a very bad situation because everybody is going to almost at the same time be accessing the centralized file. Okay, so the problem really is that our models are replicated, but our file system is centralized. Now, if I have Dropbox, and each of us has a replica of the file, no problems. And if that's part of the file system. If we don't have Dropbox-like situation, and if we have really a classic file system, then this becomes a problem. Okay. So we can have multiple computations and bottlenecks problems. Okay. And now let's go to correctness issues. And now let me go and ask the same question that I asked before, and Nick has already answered that. Is executing the same operation multiple times equivalent to executing the same operation a single time? The question before this was, is it as efficient to execute the same operation once as multiple times? And you might say if it's an add operation, yeah. But if it's something more expensive, or if it's accessing a centralized file, then it is not. Okay? And now the question is it equivalent? And Nick just said that, look, if it's non-deterministic computation, then we have this problem. So what about this file situation? Can you see? So that's one example of non-deterministic computation. Supposing our computations are deterministic, can we still have a problem? And just look at the file example as a clue to what kind of problem might occur. So we have multiple models accessing a single replica of a single file. Here we are reading. Reading is no problem. What if we are writing? Reading is a problem in terms of performance. Writing is a problem in terms of you're smiling?
Consistency.
Sorry?
Consistency.
So what's going to happen now? If you have, so let's go and see. Change read to write. So user says input B, you write to file B, and it becomes AB. That's what you want, right? And what might you get with replicas? Right? More replicas there are, the more B's there will be. So the problem is not just with non-deterministic operations. What is the general characteristic we have in this operation and in the case of non-deterministic operation? What's a more general way to describe the set of operations that we can't support? Actually, basically operations that when executed multiple times are not the same as, do not result in the same state or do not get the same result as executing them once. Okay, so the technical term, so behavior centralized, is idempotent. How many of you have heard this term in mathematics? Idempotent. You have? Forget that definition. Okay, this is a systems definition. The first time I saw it was in a thesis from Carnegie Mellon on remote procedure call. And idempotent operation is an operation that has the property that executing it once is not the same as executing it multiple times. Okay? So we can say, well, let's not make our programs non-deterministic. Okay, so we'll make that assumption. So basically what we have to do is say that in replicated case, we assume only idempotent operations. Okay, and let's try to figure out whether this is a reasonable assumption or not a reasonable assumption, and to see how many times what kind of applications we might violate this. Okay, non-deterministic ones violate it. The ones that access a file, centralized file, violate it. So this problem we could again by having replicas of the file nodes. Okay, assume that we have Dropbox. Assume each of us writes to our Dropbox copy. Assume also that Dropbox is smart enough that when two files are identical, it does not create a conflicting file. It could be smart enough. I don't know whether it is smart enough or not, but it could be. I mean, that theoretically, just do a little diff. Okay, especially if it's a text representation. Even if it's bytes and the bytes are represented the same way, you can do a little diff. Okay, so. Yeah, we won't do non-deterministic. We won't do very fancy computations. We'll have replicated file system. Can you still think of a problem? Example? Any other example where you can't just solve the problem? That may be practical. So I guess what I'm saying is, supposing you forget non-determinism, supposing you forget files, can you think of any application, practical, not practical, where we would have an idempotent operation? Non-idempotent operation.
And if it's an empty file and all the models are trying to empty file or something, no matter how many times you empty it, it's
but the result of doing it once is the same as doing it multiple times, right?
yeah, exactly.
So you're right that if they're trying to empty a file and it's already empty, the file is a no-op, the operation is a no-op. Yeah. But the operation is a no-op if it's done once or n times. So when you guys learned programming, were you ever told not to have side effects? Right? Side effects, when you have side effects, then those side effects can occur multiple times. And so this is an example of a side effect, a file changing out in the database. And imagine sending mail together. By the way, this is one of my examples I use in my papers. Is that something you think is practical, composing mail together? Mail is a collaborative tool, but how about composing an email together to send a message to me? Slow down. Give us fewer assignments. Give us more assignments. You want to word it perhaps carefully, and you don't see that, but you can imagine having a mail tool that allows you to collaboratively send mail, right? You like that example? Anybody? No? So anyway, assuming that's a practical example, somebody mails a message. Okay, the mail server sends the mail, and if you have multiple replicas, if you think spam is a problem right now, you have even a bigger problem. And imagine if that side effect is printing a check and mailing you and sending it by snail mail. The more collaborators there are, the more checks you get. Okay, so these are all examples of side effects. Okay, and these side effects have the property that multiple execution is not the same as one execution. Okay? Unless the bank says, okay, if you've got the same check from the same person, the same value multiple times, I'll just think it's the one check. Okay? So printing a file. Now that is something you might want to happen. Each one of us may want to have our own copy of the file. Okay? But this maybe you don't want to have. Okay. So we do not always have the option of replicating resources, and we can't always replicate the mail server. Theoretically, it's possible. So again, the strong assumption is that we have only idempotent operations. Okay, so we don't allow such operations. So here's sort of the summary, that we have consistency issues of causality and concurrent operations, where we try to make it look as if they execute the same sequence of operations. But even if we make it look that, we have correctness and performance issues beyond that. Okay, that's the summary. So we've dealt with the replicated architecture. We know there are some pros and cons. There are some cons at least. The pros we'll see after we go and see the alternative. But the alternative is to motivate the fact that we have these cons. Okay. And the centralized architecture seems very easy to describe. That we have interactors that share a single logical model, which also happens to be a single physical model. So how wrong can we get now? Okay, all we have to make sure is that the operations go from the interactor to the model and back, and we are fine. Okay, and most implementations you will see go here. Even though what you guys are doing in your class is replicated, because then there's a lot of advantage. And Dropbox is replicated. There's Live Meeting, which has replicated objects. WebEx has replicated objects. So I won't say that replicated objects don't exist, but the default is to when in doubt, you sort of support them centralized. So all Google apps are centralized. Okay. That's also because it's web-based. Okay, so when we have this situation, we'll talk about three kinds of members. The interactors who are just showing the UI, we'll call them slave members, and the model that is being shared, that's also a session member. We'll call that a master member. Okay, so there's no connotation here. It's just the terminology that's been used. Okay. So let's look at the algorithm. In the single user case, whenever user input I, the local model did a list. The local application did listed at input, listed at mail, listed at notified, observed, and displayed. And now we saw what happens in the replicated architecture. Now what happens in the centralized architecture? So the input is going to be processed by the slave or the master? Interactor is in the slave. Okay? So it's going to be processed by the slave. So the slave is going to do the list edit input, and what's going to happen here? There's no local model. So what should it do? Send to the master. See, you guys are all interacting today. Isn't this great? This really is great. Okay, so send list edit to master. Okay, this is the slave UI thread, and now we have to consider the master receiving thread. What is it going to do? For each list edit received R, it's going to make the change, but no notification, no observation. It's going to go in now, send to others. Okay, so this one is unicast now. Even though we are a group application, this is unicast. This is multicast, right? And for slave receiving thread, for each list edit received R, we're going to display them, right? So this loop, this sequence of actions just became distributed. This is just, this is sort of classical distributed computing, except that there's an others here, that the action is going to other collaborators also. It's not just coming back to you. Okay? If it was classical distributed computing, imagine that you're doing computation of prime factors. So your interactor just goes and takes the input, gives it to a supercomputer, gets the result back. So then here it would be list, edit, send to reply. There'll be a reply operation here. The reply operation here has got replaced by an others, which means the other people also see the prime factors. Okay? So that's our algorithm. And we have none of the replication issues. Feedback, but what's the problem? My feedback involves a round trip. What about feed through? You guys remember what feed through is? Feedback is the time it takes for my input to cause output on my computer. And feed through would be other computers. So for feedback, I have an extra hop. For feed through,
Two hops.
so also an extra hop. Okay, we have two hops, and if we have a relayer, we have yet another hop. Okay, so it goes from interactor to model to interactor. Okay, so that's the con, that's the disadvantage. The advantage is things are safe. When in doubt, centralize. Okay. Okay, so maybe that's something we have to live with. But here's something else. Here's a thing that supposing, look at the history example. Okay, sure, when I entered the input, to get my echo back, I have to go to another computer. But what if I just do the history operation? I want to just do a query, a pure read operation. I still have to go to the other computer and come back, right? Can we somehow solve this problem by having a little variation of this architecture? Right now, all my model operations are going remotely because there is no local model. Yeah.
Do you want to cache?
Remember when I asked you guys earlier, what are some generic solutions you can always apply? Indirection, caching, right? So I would like to somehow cache the centralized model locally. Okay? So caching is a solution. Okay? So what I'm going to have is I'm going to have a model and a model cache. And suddenly this becomes a lot like replicated architecture, right? You have a model locally also. So let's try to understand what is the difference between caching and replication.
So operation is made by the master, not the local machine.
The operation is made by the master and not local.
Yeah.
But if it's not made by the local machine, then how can I get my history back? How can I get some state back?
The master refresh the data, it will notify the local machine, and then the cache will
Okay.
get the new result.
So all caches are guaranteed to be consistent with the master. Right? They get updated after the master gets updated. In the replicated case, you change this and then you change everybody else. Okay, and there is no central guy that is sort of a reference point. Here, this guy is a reference point. And so what's going to happen? And we'll assume that model cache is a data repository without side effects. Okay, it's just got state in it. It doesn't go and print checks. It doesn't send emails. Okay, it's just got the query operations that you can query, that you can use to query the state that is stored there. Okay, so they're not the same class of object necessarily. In your IM case, they can be the same class of objects because this it's pure state. Okay, so the interactor goes and changes the model, right? The model goes and tells the cache it's changed. Now the cache changes itself and tells, and so no divergence of caches. Real model has the real state. Okay? And the model cache can then go and tell the interactor, I've changed, and the interactor can then go and query the cache and say, okay, what's this value, what's that value, what's that value? Okay? And like real model, it can fire events to local observers. Okay. So in fact, this is nice. The interactor. Okay. Okay. So we'll talk about this a little more. So write operations take round trip time. Okay. But read operations access local data. Okay. This is a principle you'll see in distributed computing in general, and we've applied that to collaborative computing also. Okay. All your proxy web servers, which are not collaborative, they sort of use this principle. Okay, so we've improved the architecture, and we're going to improve it even more. So let's talk of awareness, distribution awareness. We said that, look, we are building a distributed application. I've given you a session management library. Hopefully it's easy to use. Okay, but I spent 3 hours describing it. And we'd like different programmers. We'd like some programmers to be able to program without referencing it. Okay? And if we change the library, we'd like to isolate the changes to your application to a few modules. Okay? So in this case, let's talk of distribution collaboration awareness. Okay, so we talked of awareness and transparency earlier, that a module is transparent to something if it's oblivious to that thing. Okay? So a module is transparent to distribution if it does not even know that there's distribution going on. It's oblivious to collaboration if it doesn't know there's collaboration going on. Okay? The moment you use my library, the moment you use RMI, you are collaboration or distribution aware. So our centralized model, is that collaboration distribution aware? Does it know there are remote objects around? Yes, because it sends to others. Is that interactor, anytime there's arrows between a module and another process, you have awareness. Okay? The interactor sends the value to model, it's distribution aware. The cache receives objects from the model, remote model, it's just aware. All 3 objects are aware. Now, if you're using my library, you're not using something higher level, that's a fact of life. Somebody will have to be aware. In general, if you're providing collaboration distribution, some component of the whole system has to be aware. Maybe the libraries are aware and the application is not aware. That would be great. That would be your next project. Okay? But if you are using the session management thing, some code in your application has to be aware. So can we go and reduce the awareness somehow? Can you go from 3 to 2 or 1? Yeah.
Why does the model get to write directly to the model cache?
Why did I make the arrow this way rather than go back to the interactor? Anybody want to answer that question? Performance, because you're caching data. So it could send one message to the model and one message to the interactor, but then 2 messages went to the other site. So we have to do 2 things when the model changes. We have to update the interactor, and we have to update the model cache. In my first architect picture, we didn't need the cache object.
Yeah.
But in this picture, we do. But I made this picture so that we could have performance. And now let's go and say, now we have 2 modules that are aware. This object has to be aware. We can't get rid of awareness here. Can we reduce awareness from these 2 objects to 1 object?
We let the interactor interact with the model and the cache, and let the cache to update the model instead of just using the interactor to update the model.
Okay, beautiful. The interactor updates the model cache. The interactor doesn't even know there's a remote model. We tell it, this is your model. We give it the cache object. It says, oh, I've got a model. I can invoke operations on it. I can get events from it. And that model then goes and updates the real model. So my cache is now not only a cache, but a proxy. Okay? So this is the problem. And so interaction, all of this I said earlier. So the solution now is that we have a model cache slash proxy. Okay. So interactor says, oh, you're my model. Okay. Says, not really. It knows that. It sends a message to the central model. So it's a proxy, sends a message back, and the read operations still operate as before. Okay? Questions? So less distribution awareness, and we'll see that this architecture will allow us to automate this. This can be automated, actually. This whole thing can be automated under certain conditions. Okay, so model cache is still distribution aware, both sending and receiving messages, and we'll try to fix that problem also. Okay, and like I said, if you're using a general purpose communication layer, some distribution awareness is necessary. You just can't avoid it. Okay, and if we get time, we'll talk about getting rid of all of this awareness. Okay, if possible. So my no caching algorithm is that you send, I should be followed by matching list edit input and list edit send to master, and all this stuff occurs. And now what I do is I do list edit input and I do list edit forwarded to the proxy. Okay. That's what's really happening. To the interactor is just making the operation. But the proxy is really saying to the tracer, I forwarded the operation. I didn't really make it. Okay? And the slave proxy then goes and sends it to master via, and it sends it to master. And then, of course, the same sequence of actions occur here. Nothing changes. And the only difference is that when the slave receives the operation, it goes and makes the operation in its own state also. Okay, that's what the cache is. And rather than just going and sending the operation to the interactor. Okay, so now the receiving is being done by the cache, and it's updating the state also. Okay, and this is for list edits. You can just go and change all list, that's global substitute all list edit to edit, and make this a very general algorithm, saying there is some write method, write methods cause edits, and that's what they do. Okay? And just to make this all very concrete, in our example, if we have 3 users collaborating, if we have n users collaborating, we had n plus 1 processes before. Now we have n plus 2 processes. Okay, because we have a process for the model also. Okay. And let's just make this look. So see what happens. So input arrives. Normally you would go and do element added to history. What are you going to do now? Proxy add. Right? To client, received by the master. Centralized add, it does some kind of add that just changes its state. Sends the data to others. Received by the slave. And what's it going to do? Okay, now here's an interesting point. When you receive a message, you get an identity of the user who changed it, right? What will be the username here? No. It's always the message. No, who is the username? In the session manager, if the user, oh, you're saying it should be the same slave. It should be this. Since this is the user that made the change, it should be this user. But the session management library got the message from which process? Master. So it's going to be the master. So everybody's going to think every change is going to be made by the master. And in your example, you have to go and take the change, append that to prepend that to the text. So our application won't work if we just do this. So in this case, because we have these funny semantics, and I added these funny semantics just to show the boundary conditions, what should happen now? How should we support our application?
Like the change from the master has to be communicated to our cache history, because other users making changes would also appear as changes from the master. And so we can't just throw it out. It could be a change from a different user.
Okay, so the change so my change did go to the master. The master, when it did an add, it said, okay, send back this text, okay, and they send back the echo. The echo has to be attached to the user who made the change. And so if you just go and say, okay, here's the echo string, send it across, then this slave coupler will think that the change came from the master. And what you're saying is that the master has to do what now?
I'm saying if the slave coupler thinks that the change came from the master, then it has to forward it to the slave history. So either we change the message the master communicates to the slave that says this was the user that originally made the change, and that's probably the better option.
And the other option is?
Would be to add some sort of functionality to the history to detect whether or not this change is a change it has already made, which that gets messier.
Okay, yeah.
And I think the master can distinguish well this message control and don't forward this message to the user who sent it.
Okay, so you guys are saying three different things here. Okay, so and one thing is correct, which Nick pointed out. So there are three different issues. One issue is when I make this change, should I even get the change back? You're saying no, you shouldn't even get the change back. If I don't get the change back, then I will not. Remember, this is the change first goes to the model. Model decides what the echo string is. In our example, it happens to be the same. But I could take a lowercase string, the model could take a lowercase string and convert that to uppercase. It could go and add some nice fonts around it. It could do many things. So the slave must receive the input back. Okay, that's one problem, and we do want it back. Okay. The second problem is, how do we avoid bounce backs? Okay, how do we avoid the thing just cycling around? And that was the solution that Nick was proposing, that look, the history detects that the change has already been made, so we don't go and remake it. Okay? The third problem is that I need the signature. And like you said, when the message went to the master, it knew who it came from. When it sends the two others, it goes and sends, it has to do the extra step and say, look, this was the original user. And that is the object it sends to communicator. It doesn't just go and send the string, it sends a signed string. And that signed string is what the slave coupler looks like. The slave coupler just ignores what the string that the communicator gave it. Okay?
I think it's especially important that the master gives a response to the slave, because that allows us to, the master has the authoritative record of the model, and that allows us to implement some functionality that the individual slaves might not be aware of. Like say the slave tries to submit some change to the master and the master rejects it.
Right. So exactly. And so we do want things to go through the central process, because the central process might have computation, might know better. Another way to say that is that the slave is just an interactor. It can make no decisions in life. All it can do is process input, display output. The computation decisions are all made by the model. And there is only one model. Okay, the slave can't assume that what the user input is what the user is going to see as output. And that's what I was saying, that you might want to make it lowercase or whatever. So it has to come back from the model, and that is why it's not a replicated architecture, it's a centralized architecture. The local model is just a cache without any intelligence or computation. It's only got data structures that are cached for read. Okay? So I'm just saying that this architecture seems very simple, but it's messy. And the most important point is, so master puts name of original sender in marshaled edit operation, used by slave coupler to compose new element value. I'll try to remember to change this. Okay? And so then it goes and makes an add operation there. Okay? And just to make this all very concrete, let's go and see the difference between replicated add and centralized add. In replicated add, I went and did the observable add locally. Okay? And then I sent to others. That's what my replica, the replicated ad was. In the so this is the list edit that I sent. I sent a list edit without any signature of the user who made the change. Okay? And this latest list edit was serializable. Now my centralized ad is in the centralized model, and it also does a super ad, but it does not do super observable ad. It does super ad because there's no local interactors observing it. Okay? And it composes now not a list edit, but a user edit. And what's a user edit? User edit extends list edit with a get username and a set username. Okay? So this is making it all very concrete. Okay? And yeah, so this is the name that's being added here. Okay? And in the slave, our proxy ad does not go in. I'll try to go and align these things. The proxy ad does not do any super.add. Okay, it's not making any change. It's composing a list edit, and it's just sending the list edit to the master. It's unicasting to the master, to client rather than to others. Okay. So when I motivated to client earlier, I said, what if you're in a mud situation where you have to go and send something only to the other guy? But to client is also motivated by the centralized architecture. Even if you're sharing the change with everybody else, you might first want to go to the model and unicast it to the model, and then it goes in. Okay? Okay, so that's okay. So we have consistency issues of causality and concurrent operations in replicated model. We have correctness and performance issues there. And in the centralized model, all updates routed through central model, so local cache is guaranteed to be consistent. Each operation executed only once, so no problems on not an imported operation. Okay, but the problem is round trip delay to get local feedback. You have a central bottleneck which may not always be available. Okay, I should say feedback and feed through. Okay, so it seems that we have, these are the trade-offs you make in life. And of course, if you are very ambitious, what do you say? You say, I want to have my cake and eat it too, right? I want the best of both worlds. So let's think of that. Can we combine the advantages?
Could we have an immediate feedback where a change we make modifies our local cache?
Yeah.
And then if we get a response from the master, that the response from the master can effectively overwrite that.
Okay, that's very good.
I know what you tried to do, but that didn't happen, and the local cache rewind.
Okay, that's very good. So what you're saying is that we make the operation immediately in the cache, okay, and we send the operation to the master also, which is the reliable value, okay, and we get a response back. If the response makes our local object be in a different state than what it was originally, we somehow undo. Okay, so undo is a great operation, as we know, and in replication, in collaborative case, it's even more useful. Okay, you guys like this idea? We are being very optimistic. We'll call this the optimistic mode. We're being optimistic and saying, there'll be no problems. We make the operation locally, immediately, and then we undo it later if it was an operation that really caused problems. We don't quite know how to implement it, right? It's going to be tricky to implement. It's very, very tricky to implement. Okay. But forget that. Assume that we can somehow do it. Now, in replication, what are the issues we get? Performance issues. If we are all computing prime factors, have we solved that problem? No. We're all accessing a central file. Have you solved that problem? If you all access, either reading or writing. So all we've done is solve the consistency problems. The consistency problems, I'll show you better solutions. We'll look at operation transformation, which is kind of an undo. In fact, what you just suggested was an operation transformation. Okay, not quite. But it's not undo, but it is invoking an operation that effectively does undo. So how about non-deterministic operations and file operations and sending mails and so forth? And we don't have to just restrict ourselves to replicated and centralized architecture. We can combine them in some way. So look at file access. Let's say we're all sharing an editor. We're all editing a Google Doc. And at some point we go and save. Can we make sure that most of the time we don't have the disadvantages of centralized architecture? So we did a 2-hour editing session, then we saved. Before the editing session, we loaded. Loads and saves are problematic in the replicated architecture. The edits are not. So can we change our architecture a little bit? So what would it mean to combine replicated and centralized? Think of that. That's the hint I'm giving you. So we have a 2-level thing right now, interactor, model. Can you think of a 3-level thing? I didn't realize it was such a hard. So we're going to use causal multicast and OT for consistency, or this undo idea. And the question is multiple operation. Can I maybe make one model distinguished, like in the centralized case? Say, if I am Alice, I do these operations. And that model goes and executes the expensive operations. That's the one that executes the non-idempotent operations, and it somehow sends those results back. And this is a picture, a 3-level picture. That we do most of our changes using regular model, and things that are problematic, we do in a model. This is very application specific. That's maybe why you're not thinking of a solution. This is not good if you want to automate. But if you want to build a practical application, this is what you have to do. And if you want a practical application with replicas, that we have a supermodel that does these operations. And think of it, it's not such a funny thing. After all, these models are accessing a centralized file system. Why don't we just provide an object that goes in, accesses the system on their behalf? Okay. Questions? Okay. So the main point here is that this is application specific. So this is not a nice solution in a very general way. The architecture is general, but it's not something that can be automatically supported. Okay. So there's many ways to do hybrid architectures. This is one way to do a hybrid architecture. Okay. And I believe that in most realistic applications, you will need some kind of centralization. Okay, so then the next question becomes, can we automate these architectures? Okay, and we won't be able to do this 3-level thing, so we'll just go and focus on the pure centralized and the pure replicated architecture. And can we just automate it? Okay, and I gave you an algorithm that was very general. I said edit made, edit input, and so forth. So it seems we should be able to automate it. Okay. And for centralized, also I gave you a very general algorithm. And what I want to do now is, I want to get away from the session management layer and build on top of it, the session management layer here, and build on top of it a model sharing layer that will provide automatic support for centralized models or replicated models. And the goal is, if I have this layer, then the awareness, collaboration awareness in the application code will be reduced. We were very careful to choose an architecture that went and localized the awareness. But it did not eliminate the awareness. But because we localized the awareness, we might be able to even eliminate it or reduce it. Okay? So that's our next challenge, how to do that. Okay? And we can assume some magic. Okay? We can assume that we write our own compiler, perhaps, keeping the same language. Or we can assume we invent our own language, in which case we have to write a new compiler. Or maybe we use a language like Java, which has many facilities that you're unaware of that allow such automation to happen. Okay, so this is not a very abstract problem. I mean, I thought a lot about giving you guys an assignment where you will build an automatic model sharing system. Okay, so after the end of it, it's not that you can take your IAM application and replicate it. You can take an application that I gave you, which you don't even know about, which meets certain constraints perhaps, that you will go and replicate. That would be a more satisfying thing, right? Yes? No? The problem with that was that A, we were running out of assignments. B, I would need my grader program to really work to see whether you have done that or not. Right now, your UI, the video you create, gives me a lot of information about what you did. If I go and give you this application, I don't know whether you just went and handcrafted the collaboration or you went and used the automatic thing. Okay? But think about it, and at the end of the course, tell me whether you would have had enough time. I think the next two assignments are relatively simple. For those of you who haven't started it, I don't want you guys to delay it even more. Anybody made much progress with the second assignment? Okay. Anybody been stopped for some reason? Any thinking, intellectual problems with it? No? Yes? No? Admit it if there are. Okay. So maybe you all think it's very simple. But I think once you get the hang of it, it's relatively simple. Okay? And the next one will be very much like this, except that you'll be broadcasting different kinds of objects. So I think between these two assignments, I could have put another one in, okay, which would be much more interesting because then you could take a model and share it, but not this time. But let me know whether next time I should torture students with that assignment or not, okay, whether they'll be actually tortured or not. Okay, we'll start off from here next time. And what I want to do now is, I want to get away from the session management layer and build on top of it, the session management layer here, and build on top of it a model sharing layer that will provide automatic support for centralized models or replicated models. And the goal is, if I have this layer, then the awareness, collaboration awareness in the application code will be reduced. We were very careful to choose an architecture that went and localized the awareness. But it did not eliminate the awareness. But because we localized the awareness, we might be able to even eliminate it or reduce it. Okay? So that's our next challenge, how to do that. Okay? And we can assume some magic. Okay? We can assume that we write our own compiler, perhaps, keeping the same language. Or we can assume we invent our own language, in which case we have to write a new compiler. Or maybe we use a language like Java, which has many facilities that you're unaware of that allow such automation to happen. Okay, so this is not a very abstract problem. I mean, I thought a lot about giving you guys an assignment where you will build an automatic model sharing system. Okay, so after the end of it, it's not that you can take your IAM application and replicate it. You can take an application that I gave you, which you don't even know about, which meets certain constraints perhaps, that you will go and replicate. That would be a more satisfying thing, right? Yes? No? The problem with that was that A, we were running out of assignments. B, I would need my grader program to really work to see whether you have done that or not. Right now, your UI, the video you create, gives me a lot of information about what you did. If I go and give you this application, I don't know whether you just went and handcrafted the collaboration or you went and used the automatic thing. Okay? But think about it, and at the end of the course, tell me whether you would have had enough time. I think the next two assignments are relatively simple. For those of you who haven't started it, I don't want you guys to delay it even more. Anybody made much progress with the second assignment? Yeah. Anybody been stopped for some reason? Any thinking, intellectual problems with it? No? Yes? No? Admit it if there are. Okay. So maybe you all think it's very simple, but I think once you get the hang of it, it's relatively simple. Okay. And the next one will be very much like this, except that you'll be broadcasting different kinds of objects. So I think between these two assignments, I could have put another one in, okay, which would be much more interesting because then you could take a model and share it. But not this time. But let me know whether next time I should torture students with that assignment or not. Okay, whether they'll be actually tortured or not. Okay, we'll start off from here next time. So this would really mean that so here's an object, just an example. It's got these variables, a float variable, an int variable, and the basic idea is that whenever I go and change this int variable unit cost, it gets changed everywhere. Okay, that's what the semantics would be. We replicated memory, and that would mean that my assignment statements have to be compiled differently, and they're very costly. Okay, and this guy who did distributed memory, he did change the compiler. Okay, so it's doable, but it's probably not what you want. Okay, so things are getting hard. We've got variables, we've got methods. So let's try with methods. So we're invoking the assignment remotely, and compiler support, costly, no control of what and when, okay? No transaction support. And that's the algorithm for that particular application. In general, there would be some kinds of edits input. Okay, this could be changing a little field in a form, it could be adding an entry, it could be changing a table. So wherever there was list edit, I've changed that to edit here. And edit basically means that the model has been changed. Okay, so this is the general replicated algorithm, which is independent of the IM application. This could be used for PowerPoints, it could be used for editors, it could be used for anything. Okay, and again, we have to make sure that this cycle doesn't matter. Okay, so the previous slide was about this replicated architecture, and the key there was that we had to somehow figure out what the edits were. Okay, and we said that, look, we are going to use maybe a keyword or an annotation. And same kind of stuff we want in the centralized architecture also. If we can somehow figure out that, what we want to automate here is that once a proxy edit has been made by the slave, we want to be able to go and automatically make an edit sent to the master, okay? Receive the edit in the master, send the edit to all the slaves, okay? Receive the edit in the slave, make the edit in the slave, and then we're done. Okay? There's much more work to be done now. But again, it just means we have to generate some proxies. So again, all of the operations to be automated are the ones I showed you earlier. The operation that triggers these is this edit forwarded. And you can not only intercept methods, replay methods, you can create proxies of your own. Okay? And in Java, you can do that just using the language. But if you didn't have the language, you could write your own pre-compiler that generates the proxies. Okay? So before Java was invented, I mean, that's what people did. That's what I did, for instance. And so you can do all these things. Okay, so the key is the same distinction that we're trying to make. And like I said earlier, that a lot of people came up with these eureka moments that, oh, we're going to have, and what we're going to do is somehow make a distinction between the write and the read methods. And the write methods we want to replay at the other end. Okay, this is the case. This is in the case of replicated architecture. Similar kind of logic follows in the centralized architecture, and the read methods we don't want to replay. Okay, so in the case of proxies, the read methods are just executed on the cache, and they're not forwarded. The write methods are forwarded. So somehow we want to distinguish between the read methods and the write methods. Okay, and so we don't want this to happen where the read method is set across the network. So need a way to select the methods to be broadcast. And we will just have a broadcast keyword, okay, or an annotation. Okay, and like I said, lots of people came up with this idea, and the first ones to come up with this idea would have come up with this idea in which decade, you think? '70s? That's ancient enough for you? When do you think the first collaborative application was built? Synchronous collaboration, where one screen is being shared with another screen.
Late 60s?
Did you just guess?
Like a long shot.
Wow. Anytime you guys want to buy a lottery ticket, contact Nick. He's good. Okay? He's good at long shots. So there was a guy called Douglas Engelbart. Anybody heard of him? You have?
It sounds familiar.
So when was the mouse invented? '60s, by the same guy. Okay, and he did this conference where he showed all these things, and he's won the Turing Award, and he was in a company called Xerox, which did a lot of pioneering work. And if my memory is correct, he was too advanced for them. And Xerox was too advanced for the rest of the world. Okay? And so that was '60s. This was done in the early '80s, so you're pretty good too. At Xerox. Okay? And there was a system called the Collab, Xerox Collab, that built a lot of applications. And the underlying infrastructure for that system was this language. Okay, and many of you, Java. Okay, its predecessor is a language called Mesa that was also invented by the Xerox guys, and this was done in the context of a Lisp language actually. So Xerox guys did the Lisp environment, they did the programming environments, they did a lot of good stuff. Okay, so this was done there. And they basically had a broadcast keyword, okay? And a broadcast method was executed on all the other replicas also. And they made sure that you didn't have a cycle, okay? I'm sure that was part of the challenge in your current assignment, to make sure that you don't have a cycle of execution of write methods. Okay, so they just took care of that for you. And things that were not broadcast, were not labeled as broadcast, were not broadcast. Okay? Simple idea, pretty effective. Okay? Questions? They had their own language, so they could intercept the broadcast methods and they could replay them at the other end. So, can anybody see a problem in this picture? I've changed things a little bit. Can you see the title here, spurious broadcast? What could that mean in this context? It's some broadcast you don't want. So I have broadcast here, okay, and I have broadcast here also. And this is a notify method. Okay, a notify method is typically called by a write method. So can you guys see what problem might occur here?
So if we call set ticket price
Yes.
on the upper model,
Right.
then that will cause that call will be replicated, and the bottom model will call set ticket price.
Right.
set ticket price calls will call their respective notify calls, and then one of those will be broadcasted. So notify will be called twice. And
Twice.
Bottom.
Perfect. Okay. So we call the broadcast method here. The broadcast method here is also called. The broadcast method in the top model calls the notify method. So the notify method is called once because of that reason, and once because this particular method was called. Okay. So of course, stupid programmer, they should know what they're doing. And the question is, how easy is it to be stupid in this way? Well, that paper said that it was easy to be so. Okay. That's one problem here. That the system is not asking you to distinguish between right methods and non-right methods. It's saying make certain methods broadcast and certain methods non-broadcast. Whether these methods are right or not, who knows? Okay? And they were in fact not targeting model sharing. They were targeting, so you must be careful. You must carefully choose which methods are broadcast. And they were not just focusing on model sharing. You could make interactor methods also broadcast. Okay? So when the text change method is called on your interactor, you could call the text change method on other interactors also. So you could share not only model state, you could share UI state, and in fact all the applications I saw of this particular language were all doing UI sharing and not model sharing. Okay? What kind of sharing you should do is yet another issue, and we'll get into that soon. So you can broadcast methods in any object, not just model, and that's why notify method could also be used as, could be made broadcast. And in Xerox Collab applications, so interactive methods were indeed broadcast. And so then the problem is that if you use the model interactor paradigm, and by the way, the model view controller, which I've approximated to model interactor, was also invented by Xerox guys. Okay, they invented it. They put that in Smalltalk, and nobody knew about it. They were going to write a book about it, which they postponed writing. They wrote one obscure paper, and the reason why I know it and why it got popularized is there was a guy at Illinois called Ralph Johnson, named Ralph Johnson, who looked at Smalltalk code to just find ways in which object-oriented programming is done. Okay, because they kind of did the first real object-oriented language. Smalltalk, many people think, was the first object-oriented language. Actually, it was not. The first object-based language was invented in which decade? Anybody want to guess? 60s. Language called Simula 67. Okay, invented the Bell Labs. It was object-based, not in object-oriented, because it didn't have inheritance. But it didn't capture people's imagination. Okay? Smalltalk is the one that captured people's imagination. That was the language that was used to create an environment. That was the language used to create model view controller. And Ralph found this out. Ralph was in Illinois. I was at Purdue. And we talked, and he told me about it. So I started telling people about it. And then, anybody heard of Ralph Johnson? Anybody seen that big design patterns book? The Gang of Four? Ralph Johnson is Gamma, Johnson, and I believe Ralph Johnson was the brain behind that book. Okay? So he was the person who was trying to look for design patterns in Smalltalk, and he found model view controller there. Okay? So they were probably using this pattern in even the Xerox Collab applications. And then the problem becomes that you've gone and made text change broadcast, somebody else goes and makes set ticket price broadcast, and then you have again spurious broadcast. Okay? So this is the problem. And so you guys want to fix this problem somehow? Say we are only concerned with model sharing. We're not going to look at UI sharing. And the problem, like I said, was that they did not ask the programmer to say what the right methods were. They asked the programmer to indicate what the broadcast methods were. So is there a better way to explain the right methods? So if you were to look at this model, so in general, firstly, can you build a tool that looks at some arbitrary object and figures out which of its methods are read methods and which of its methods are write methods? No? Why not?
Unless there was some sort of, well, you could try, but unless there's some sort of annotation on the part of the programmer, you could look at signatures, we could look at names. That requires that the designer follow some sort of convention.
Convention. Okay. Otherwise, an object is a black box. Right? That's the whole point. You just look at the method signature. It provides some method signatures, and some documentation might explain what it means, but a programmer is free to choose whatever they feel like. Okay? Unless we go and provide an annotation. Annotations, you still have to put annotations. Better than that would be to follow some conventions. Okay? And if we look at this particular model, and we don't know anything about what the programmer did, but from this method name, we know it's a write method. It's a setter. And we follow these conventions. Okay? So what's another solution to select methods to broadcast? So we somehow need to distinguish between edit and non-edit model methods. And in general, an object is a black box. We do not know its write methods without explicit programmer specification. But we can restrict our model types. So what are the solutions? One is, what Nick pointed out was a more general solution than the first one I'm talking about, which lots of people have implemented, is that we say, look, what are interesting types? I mean, array list and vector, they're just so popular. Hash table, hash map, they're so popular. So why don't we go and provide replicated list, replicated table, and maybe you solved 80% of the problem, okay? Or maybe less than that. Because what about a bean? What about my concert expense? That's a programmer-defined type. And this solution does not allow programmer-defined types, the types that programmers themselves create rather than what the language provides, to be replicated. Okay? So in that case, so we can't deal with beans, and we cannot deal with any programmer-defined types. Okay? And that is when we go and say, hey, let's go and use some patterns, some conventions. And these conventions are meant for the humans, of course. Okay? But these conventions can also be used by tools. And that's the key here. That we go and use these conventions to replicate operations. Okay? And so this is still restricted. Okay? But just as we can define conventions for beans, we can define conventions for lists. Okay? We can say that the list must have a size method. If it's going to have an add element method, it should be named add, and it should take as an argument the element type and then the index. Okay? So we can define these conventions also for tables, and then we can define our own lists and tables. We don't have to take array list or hash map. We can define our own implementations of these. We don't even have to use their interfaces. As long as the interfaces follow certain rules, okay, we can automate that. Okay? And there's all kinds of facilities in programming languages, in particular in Java, that allows us to go and extract these patterns out, to go and figure out if a class follows these patterns, to find methods that follow certain patterns, to go and use that extracted information to actually invoke those methods. So there's a lot of interesting stuff going there that we can use. Okay? But it works for at least a theoretically restricted set of model types. You can say that, I can dream up all the kinds of objects you'll define and define conventions for them. But of course, you can't always dream up things. Okay? So I just want to indicate that this is not without any con. There are cons here. Okay? Okay. So we've gone and dealt with one issue, which is how to determine which methods have to be broadcast. Again, we saw two solutions or three solutions. One is we have broadcast methods. The other is we fix a set of types. And the third is we fix the set of patterns. Okay? And the other question, and this is the question you guys will have to deal with in your next assignment, is how to find corresponding replicas. Okay? So we know that set ticket price here has to be invoked on set ticket price here, but how do we go and figure out that this replica corresponds to this replica. In your assignment, how did you figure out that when you receive a change, how did you figure out which object the change should be made to? The type. And how many instances of that type were there? One. Okay. Nick?
So you meant based on like messages that we receive, how do we know which changes to make to the model?
Or which model to choose?
Well, I had the models that models were listeners, I think, in my implementation, and so models would register to be notified for relevant.
Okay, so that's good. So that's what happens. That your replica was a listener to something else, so that it could change itself. But if there was more than one listener, so was there only one listener that could take a change? So the question is, which model should the change really be made in? Forget how it's done. Just figure out which model should be changed. And Patrick, right? Patrick, right? Okay. So Patrick said that there was only one model of that type, so there was no choice to make.
Yes.
Okay. So we could make the same assumption. We can assume that model classes are singleton. Okay, singleton class is a class that's instantiated only once. And then our problem is solved. We go and figure out that this set ticket price was invoked. We know what type it is. We figure out at the other end some instance of that type, or the only instance of that type, and we can somehow enumerate all the objects, and then we go and make the change on that model. Okay, this means we have to somehow enumerate all the objects, which is not easy. Okay, and secondly, we have to make the assumption that model classes are singletons. Can you think of some other way? You can use to automatically figure out which model to make the change on. In your case, you guys just make sure that the right model was listening, so there was no problem. Yeah, Nick?
Is there some way that we could make sure each model has a unique ID?
So we could go and put in each model an ID.
That seems doable in a more centralized solution if we have a centralized broadcaster.
Okay.
Otherwise,
But you know that in Java there is a hash code in each object. Would that work?
not necessarily.
Not necessarily, because.
We define a good hash function.
Oh, so there is a unique. Let's just put it this way. There's a unique. I shouldn't use set hash code. There is a unique code in each object. Could that be used?
I think so.
You think so?
Because this function exists in the object type. That means every type in Java should have that function.
Yes. Every object has that.
You can overload that function and, like Nick said, design a new hash algorithm to basically go to the get hash code returns the unique identifier for that specific class.
Okay, so we do know that Java has a function. By the way, Java has two functions. One is the hash code used in hash tables, and the other is a system identity code, and that is unique. Okay, the hash code can change based on its contents. So why do we? So let's assume that by magic the language has a unique ID. Do we need to overload that ID then? Do we need to overload the method to give our own ID? We don't, right? It's unique already. But how do I know that this replica corresponds to this replica? Each JVM gives its own IDs. These IDs are not network-wide and same.
There are UID
So use some URL.
that are considered as worldwide unique.
Sorry? Okay, so there are algorithms that you could imagine that will generate unique ID for everybody, and so that would mean what? That would mean that based on the content of the object, these two guys have the same ID, or do we go to some central guy? Go to some central guy to get a unique ID. Okay. So that could be one method. So by the way, the Xerox paper doesn't describe how these two guys are, how these two replicas are bound to each other. Is there other solution we could use also, besides going to some central server? Because the content of the object is not going to be able to. You know, there's no way that you can figure out really that these two guys are the same object based on just their contents, because there can be so many objects with the same content that are not supposed to be replicas. So we have to go to a central guy, or some authority. Is there any other way? Assume that each program here, each replica is created in the same program. That means assume that this programmer, the process in which this replica exists is executing the same program as the process in which this replica exists. That was what an assumption in Xerox. Okay, that we take one program, we just execute it in multiple sites, and that program is not even aware that it is replicated, and automatically accept that there are broadcast methods. I'm sorry, it is aware. Okay, and the broadcast methods are tied. So if we assume the same program is executed at all sites, can we use that semantic somehow? Can we use some information? Suppose we can also figure out each time an object is instantiated. We have our own language. We know that this object got instantiated now, this object got instantiated now. Now can we figure something out? Can we figure out an algorithm?
When the object is initiated, give them the same unique ID.
Okay, so how do I know that this object corresponds to this object? Yes, if I can figure that out, then I can give them an ID. But how do I know that this is the same object as this one? They're executing the same program.
Created by same program.
Okay, created by same program. But I can have two hash tables, two lists. And how do I know that this list corresponds to this list? Assume the program is deterministic. Reflection will give me the type. Assume that we can know the type also. But how do I know that this replica corresponds to this replica? So the variable names go away. Okay, they're just addresses. So you're saying that, maybe both objects are given the same virtual address by the compiler. The physical address will be different. You know, if we can get into that, if it's deterministic, then the objects will be instantiated in the same order, right? That means the second object here will correspond to the second object here. The third object here will correspond to the third object here. So we could use that order. Okay? And in fact, I mean that is one solution you can use in your next assignment. What you'll have to do is make sure that this window corresponds to this window. You can assume that both programs will create the nth window. The nth window in both programs will be the same logical window. Okay, so we've seen all the alternatives here. We can assume model classes singletons, assume replica programs instantiate the same sequence of objects, and we can use the sequence ID to go and correlate them. Okay, I believe that is what the Xerox guys did, but maybe they didn't. Okay, but that was my sort of first interpretation. That's what I would have done. Okay, and when you guys do the replicated shared window systems, what you can also do is give user-defined names to those. Okay, so you can say set name. So what you guys can do in the program is say set name to be this kind of button, or that kind of button. And then as your program is giving it the name, so what you can simply do is pass the names around and say that this named window is the same as this named window. The trouble with this algorithm is that what if you have threads? What if you have so many things that make things go out of sequence? Okay? Or where the sequence is not deterministic. It won't work. This is better. And the last solution is, so it can use names of Java windows. And the last solution is having a central guy. Okay? Central guy means whenever an object comes up, you say, this is my name, okay? And if there's another object of that name, please go and tell me what those objects are. So you have some kind of registry and lookup. So let's go and look at that. So you can use order of object instantiation. You can use names of objects. We can have explicit remote lookup and register. And so you have a central registry, much like the session manager. In fact, systems that provide this facility also behave like session managers. Okay? And so they're doing not only session management, where they're making sure that two processes correspond to one logical process, but they're also doing object management, where they say that this object and these two processes correspond to the same physical object. Okay? And here's what we could do. In the master case, we could create the object in some process. Okay? This is showing you how the lookup registry would work. Okay? And it could go to the registry and say, hey, I'm going to register this object. Okay? Let's assume we are dealing with a centralized architecture. Okay? Where we have the object in the master and we have proxies in the slave. Okay? So what we have to do somehow is create proxies here for this master. Okay? And what the master can do is send a proxy to the registry. Okay? And the slave can go and then look up that proxy from the registry. Okay, so I told you guys that what you've seen already in your current assignment is that you can send arbitrary objects across the network using Java's serializable interface. So you can just send the proxy across the network and get the proxy copy here. Okay, and now this guy is out of the picture, and these guys can talk directly to each other. Okay, and in fact, this is not such a foreign idea. And in the replicated case, what you would do is create a replica, send a copy of the replica itself to some registry. Okay, then look up that replica. I should have said replica here. Okay, and now the replicas can be kept consistent, and they can be kept consistent with the central replica. Okay, so you have this registry which keeps the replicas together, and it also has a special distinguished replica. Okay, and anybody remember an advantage of having some distinguished replica that we talked about maybe the last class or the class before last? So what are some of the problems with replicated architectures? Yeah, Nick?
We have the issue of all the replicas need to be kept in the same state. They need to be kept in sync, and that's a lot easier if we have a central shared replica that takes precedence over everything else.
Okay.
And keeps the master record.
Okay, so that replica could keep the master record, and so these replicas could just mirror that value, right? And we saw that if there is a master replica that defines the state of all the other objects, then this master replica is really a centralized object, and these guys are caches. So no, we don't want these guys to be caches. We want them to be actual replicas. And there was not only a consistency issue, but there were other issues also. We saw that even if every replica executes the same sequence of operations, there could be problems. Too long ago. Non-determinism, centralized resources, in general, non-idempotent operations. Okay, so we could do all of these operations that are problematic only here. So in your program, you could go and have a little code saying, am I executing in the server or am I executing it in the client? If executing on the server, then do this, else do this. Okay, so you're somewhat collaboration aware. Okay, but you're collaboration aware for a good reason that you want to do this. Okay, and this is not all theoretical stuff here. My first PhD student at UNC, in fact, did a system called Sync that had exactly this architecture and had exactly this functionality. Okay, that you could look up, register, and you could have a distinguished replica that is kept in sync. Okay. Okay. Questions? And just to make this all look more real, there's a system called RMI that anybody use RMI, by the way, here? Okay. So RMI is sort of like this centralized system I'm talking about, not quite. It has a proxy to the centralized object. It doesn't have a cache to the centralized object. So it does not distinguish between read and write methods. It just forwards all the methods. But it's got the basic architecture that a centralized system would have. Okay, and this is your registry. You go and say, here's my object, and please register it under this name. Okay, and in this case, I'm just using its class name as its name. Okay, and here's a lookup. Again, this is what you do is you get a handle to some centralized object in a centralized server, and you go and say look up that particular object, and that is assigned to now a proxy object. Okay, this is a proxy object. In a true centralized system, this would also be a cache. In a true centralized system, we would know these are read methods, these are write methods, and we would only forward the write methods. Okay, so this is not a very foreign concept, and okay. So this is what I'm saying here. It doesn't support the centralized model. It creates a pure proxy and doesn't distinguish between read and write methods. Okay. And here is some code from Sync, the system I just talked about. And you see here that you have actually a method that says replicate or lookup. What would that mean? You know, in the centralized case, I had register and lookup. In this case, I have replicate or lookup. And I get back an object.
Maybe replicated, we will create a cache in the local site. Just simple lookup, just proxy.
Okay, so this operation, you're saying in replicate you create a cache, but no, in replicated architecture we don't create cache, we actually create a replica. So this operation is ambiguous. It can either do a lookup or replicate, and I'm leaving it up to the system. So how will the system decide whether it should replicate or look up, and why do I have them combined together? We saw the same issue in session management. We did not have a separate operation to create a session and to join a session. We said join or create. If we are the first guys, create it. If we are later guys, join. Here, I don't know which, we all running the same program. I don't know whether I'm the first one or not. So I'm saying, here's a class system. If I'm the first guy, instantiate it and give me a handle. And please go and register that with the central server. If I'm not the first guy, then go and get me an object that connects to that. Okay? So that's what this is doing. And just to show you this graphically, so when you do this, at the server end, you get an instance of this object. Okay? So you have the object not only at the local end, but also at the server end. And when Alice, supposing Alice joins, Alice goes and gets that object in her view, and this particular little window, little item tells you who the other session members are, and there's no other session member. So you see here the session management and model sharing is all bundled together. This is not meant to be like the previous system I showed you, a pure session manager, which can be used for window sharing or model sharing. This is purely meant for model sharing. And when Bob joins, Bob gets another object here, and Bob sees that Alice is joined, is already there, is sharing the and then later Alice's UI after Bob does the lookup is this. Okay, so I'm not getting into details of sync. I'm just showing you a real system with some concrete UIs and APIs to illustrate the abstract concept. Okay. So, we've dealt with two issues. How to determine methods to be broadcast, how to find corresponding replicas, okay? And the more robust solution is this lookup registry-based system, but it requires collaboration awareness, and Xerox did not do that, and so in that case, you could just use sequence of objects, or they might have used some other method, okay? But it would not be very robust because there's no explicit connection, okay? Another question is the when question, okay? So a write method got executed at my local site. When should the corresponding write method be called at the other end? We know that's a corresponding replica. We know it's a write method. We know exactly what to do. We're going to execute the write method on the corresponding write method and the corresponding replica of the remote object. We know that. We have full power. Now the question is when. Now what's the obvious answer? In your case, when a list edit was made in one site, when did you execute at the other site?
Immediately after this write.
Immediately. Well, not quite immediately. Some time will go for your thread to be scheduled, for it to go across a network, for it to be queued in a router, for it to reach the other end, for the thread to be executed, but basically you did it immediately because you were doing quote unquote synchronous collaboration. Okay? But these replicated systems are useful for asynchronous collaboration also, right? Dropbox, Google Drive, all these systems have asynchronous sharing also. It's not immediate necessarily. You could be disconnected at that time. What happens in that case? Or you want to keep some changes private before you go and make them available to others. And when you go and keep some changes private and execute a bunch of changes together, that is called a transaction. So you might want to execute transactions locally. You might be disconnected, which is the most compelling reason. And transactions may seem too sophisticated for you. And so you may want some flexibility. Okay, so when to synchronize? And I'm just going to use sync as an example because it's got very flexible semantics. So you can see here that there's a button called synchronize, and you can see here there's a Boolean or a checkbox called real-time synchronize. So can you deduce what the semantics of these two widgets are to figure out, so that you can come up with some general mechanism that supports both synchronous and quote-unquote asynchronous collaboration. So real-time synchronize when pressed would mean immediately, right? So the question then becomes, what does synchronize mean? So if the button is pressed if the checkbox is false, then we will synchronize when?
The button is pressed.
So what would the synchronize mean? So that would mean that when the button is pressed, so my write method got executed. Okay? If this real-time synchronize button checkbox is on, then clearly it means send the write method immediately from the sender point of view, right? And now at the receiving end, what will this checkbox mean? If the button is pressed, and a write method arrives, execute it immediately. Okay? So the sending end, this button, this thing means that if a write method is executed, send it across immediately. And the receiving end, it means if a write method arrives, execute it immediately. Okay? And now we can figure out what the synchronize method might do. So if this checkbox is false, then obviously the write method is not executed immediately. It's buffered. So the synchronize button will do what? The write method will get, locally, the write method will get executed immediately. We don't go and buffer your local response is immediately made. Okay? The idea here is that at this point you go and maybe connect to the network. You turn your mobile computer on. Okay? So at that point, when you press this, you have a bunch of buffered write methods that have not been sent. So what will you do? Send them. Okay? And if you come in and you haven't made any changes, you say synchronize, what will happen? All the write methods that have been received get replayed. Okay? That's pretty much what happens, right, in these mobile apps today. Okay? So it's very interesting, actually. You guys know that Samsung and Apple are fighting about patents, right? And Apple won one of the cases. And encouraged by that, Apple filed another case. And I would never have known about that till a lawyer came to me and said, can you tell us more about sync? And you know why? Well, Apple was claiming some patent that, some feature that we guys had done in sync as just one of the side things. I mean, what they patent is just such trivial things that I'm not even talking about them here. And so you agree, right? Being in companies. So basically, ultimately what happened was that they dropped this particular thing. And so this stuff is very connected to mobile computing. Okay? So let's go in the next 5 minutes, finish off this discussion. So when to synchronize? When both the sending and receiving applications say synchronize, that is when the change is made. Okay? So both sides can disagree. And sending side can say real-time synchronize to execute synchronized operation when a write method is executed at the sending side. Okay? So to execute this operation immediately, okay, you say real-time synchronize. And receiving side can say real-time synchronize to execute received operations immediately. Okay? And so what is good about this is that you can integrate synchronous and asynchronous sharing this way. Okay? And in fact, the student who built the system, John Munson, one of the examples he used was a Dropbox-like file system. In fact, he implemented that, and we guys used that for a little while here. So let's go and see this working. So let's say that this site is disconnected. Okay, it does not say real-time synchronize. This site is connected, so it says real-time synchronize. This site has gone and changed the number of attendees to 8, and the ticket price is 23.5. Okay, so this write method is invoked immediately, and you get to see the total. Okay, so you know that this was executed locally. Okay, but it's not here because you haven't said synchronize. Now go and say synchronize. Oh, please don't die on me again. Okay. You say synchronize. Oh, I skipped over that, by the way. So it was slow. When you said synchronize, the change went immediately to the other side. Why did it go immediately to the other side? Because it had said real-time synchronize. Okay? Yeah.
So let's say that the sender has the real-time synchronized box checked and the receiver doesn't.
Yeah.
When the sender makes a change, what happens? Does it attempt to send a message to the receiver?
Yes. It sends to the receiver, and it's buffered at the receiver.
Buffered. So the receiver will still buffer changes even when it's not set real-time synchronized. And setting synchronized will cause it to remake buffer changes.
Yeah. So logically, that's what happens. If the receiver is not connected to the network, it's all buffered in the server.
Okay. So there is a server.
Yes. In sync, there's a server.
Okay.
But if they were disconnected and there was no network connection, then it would be buffered at the sender and to be retrieved later by the receiver. Okay? But in this implementation, we assume there's a mirror server. It's not harming us to send things to the server also because we don't wait for a round trip time to the server. Okay? And let's just finish this. So now both of these guys are disconnected and things become more interesting. This guy changes the ticket price. This guy changes the number of attendees. Okay? The top guy says synchronize. Nothing happens here. Why? Because he hasn't said synchronize. Okay? Now he says synchronize, and the value 3 goes here. So no update in bottom user. That's what I'm saying. Now the bottom user synchronizes. Okay? And the bottom user has both changes, but the top user doesn't. Why? Because he hasn't synced as yet. That guy synchronizes, and we are finally consistent. Okay? So we understand what synchronized really means. And, oh, I might even finish. So 2 ways to share a logical model among multiple users: centralized and replicated. Both involve a local interactor at each user site. In replicated, the symmetric models are used. Okay, they do both read and write methods. And they can send updates to other models without necessarily waiting for them to be made locally. So they can send updates to other models without necessarily waiting for them to be made to go and do the UI. Okay, so what I'm really saying is that you can do your local display changes without waiting for them to be executed remotely. Okay, this is very, very succinct. And the problem is you can have side effects, and so that causes problems. And that's where we need a distinguished object. In centralized, a centralized model at a special site exists, which could be the user site. Each site can cache the model for reads. And the write now waits for it to be executed remotely before giving response to the local user. Okay? And cache stores only data and has no side effects. And because there's an indirection, because you go from slave to master and back, you might have to go and sending user's identity to the server and get it back from the server. Okay? You can automate model sharing. What you really need to do is to identify methods to be broadcast. You can have a broadcast keyword or an annotation, as Nick suggested. You can have cascaded broadcasts, which you want to avoid. You can fix the number of types that are replicated. Okay, so there's no programmer-defined type such as beans in that case. Or you can use conventions or patterns, in which case you've restricted the models. And there are trade-offs, cycles versus restricted models. And connecting corresponding objects is an issue. We just looked at what some solutions are. When to broadcast is an issue. We just looked at this solution with explicit and implicit sync, which is a very general solution. And let me just take 2-3 minutes. So Xerox Collab had broadcast methods, immediate execution, implicit replica binding. Okay, that's a system that I talked about. I'll give the references in my slides later. Sync used patterns and predefined shared. It had patterns, it had predefined types, and it could also allow patterns. Okay, so it had both ideas. Live meeting, which is a system at Microsoft. Live meeting was a system called Park Place at Xerox. And when Microsoft was buying it, I was actually at Microsoft, and I was in helping them with the acquisition. So I actually looked at the code, and this is not advertised much, but it had many predefined shared types. Okay, so it was a very nice system that way. Google Hangout, I just looked at the API, and from what I can make out, it has a single shared table. That's it. You can't have multiple tables, just some key value pairs that can be shared. Okay, so this idea is not completely foreign. And what comes next? So we've done model sharing, and what we want to do is non-model sharing. Okay, we want to justify why we want to do sharing other than model sharing. We want to justify why we build this general layer that can do multiple kinds of sharing. Otherwise, you could have just used sync and not even bothered about any other system. So that's our next thing. Okay, and that's what your next project will be about also. And hopefully by Wednesday, I'll give you enough details to do the project, and then I'll take probably a week to go and talk about the theory behind it, about the theory behind the whole area of that kind of sharing. Okay, so I'll just give you enough details to start off, and then we'll go for the broader look at the area. Okay, thank you.